Okay, so I'm very pleased to start the third day of presentation of the fall session of the CECAM workshop, Advances in Electrostatic Calculation, the Road Towards Exascale. The speakers of today are Dr. Franziska Nestler and Dr. Ivo Cabascio. The first speaker is Franziska. She got her diploma in 2012 in mathematics and chemics at the University of Technology. In 2018, she got a PhD in applied functional analysis. And since October 2020, she's head of the BMBF Junior Research Group for Fast Algorithms for Explainable Recommendation System. The title of our presentation of today will be P2N FFT, a versatile tool for computing long-range interaction in particle systems involving charges and dipoles. Thank you, Franziska, for being here.
So, okay, thank you for the introduction. Now I start sharing my screen. So I think I hope this works now. So just let me just arrange my windows a bit so that I can see what is happening here. Okay, so let's try out if this works. Yes, fine. So yeah, I thank you very much for the kind introduction, and also thank you for coming to this talk today. Thank you to the organizers for giving me the chance to present something here. I'm going to present today a method which is called P2NFFT. It's a particle mesh method allowing for fast computation of long-range interactions in particle systems involving charges and dipoles. So it's also very similar to the well-known P3M method. And I mainly want to explain the basics of this method. Yeah. As it was already said, so in my PhD time at the Technical University of Chemnitz, I considered these long-range interactions and this P2NFFT method. And nowadays, I switched a bit topic, and I'm now working with the junior research group on the field of high-dimensional approximation. So I am nowadays not working with these particle methods, but I am still in contact with these things, and I'm happy to present it here. This is also joint work with Michael Hofmann and Michael Pippich, who were also in this GAFACOS project. Maybe some of you know them, but these two guys, unfortunately, they are not longer in the university business. They left and went to industry. So also the experts for the documentation and for the programming, for the codes, they are gone. And yeah, and this is also joint work with Daniel Potts, who supervised my PhD. I will now start with a short introduction, and then I will explain the basic building blocks of the method. This is on the one hand, the eval summation approach, which is, I think, well known to most of you. And then we have some methods from Fourier analysis, mainly the non-uniform FFT or non-equispaced FFT, and some related methods. And these three building blocks then give this particle-particle NFFT method, or the shorthand notation you can see here. I present to you the basic features, what you can do with the method, and I will also give you some ideas concerning numerical results, but it's not the main part here. And in the end, of course, a summary, and you can also ask questions or discuss a bit on these things. So what is the basic problem we are looking at? So at first we look at the quite simple Coulomb problem, where you have given n charges, qj, sitting at some arbitrary position in three-dimensional space, and you are, for example, interested in calculating all the electrostatic potentials for these particles. And you all know that you have pairwise interactions, so you need to consider all interactions between all pairs of particles. And if you would compute it naively, then you will have arithmetic complexity of n square. And this is not what you want to have in applications. This is not quite efficient. And in many applications, you even look at more complicated things like, for example, 3D periodic boundary conditions, where you assume that your particles are distributed in a small primary box, and then you assume that the whole space is filled with periodic replicas of this box. And now, of course, each particle interacts again with all the other particles in the little box, but also with all other particles in all the periodic images of the box. And so the electrostatic potential, it mainly remains the same, but you have here an additional sum running over the set S. Here you have all integer vectors in set 3, and they then appear here as translation vectors multiplied with the box length. So the box length is this. And then you even have this a little bit more complicated expression. This is an infinite sum. It's even only conditional convergence. So it's also, from a mathematical point, interesting to look at this. So you have to be aware of summation orders and something like that. So this function here, this is not continuous at 0. So you have to exclude all terms where this norm can get 0. This is, of course, clear. A particle is not allowed to interact with itself. So you have these types of periodic boundary conditions, and we are concerned with the question, how can we approximate it in an efficient manner? And we also considered the following. So for now, we only had charges in our particle systems, but we started working at this and said, okay, we also want to deal with dipoles. So there were some methods for charges and there were some methods for dipoles, and we said, okay, we want to have both. So you have a set of NC charges and of ND dipoles, where now the dipole moments have to be given. And in this system, you also have, besides the interactions between charges, you have also dipole-dipole interactions and mixed interactions between charges and dipoles. And how to do it? So what we did, you can formally replace these charges from the last slide by these operators xi j. In case of a charge, it's just a multiplication with the charge, but in case of a dipole, you have these differential operators, where you have to compute the gradient with respect to the particle and then computing the inner product with the dipole moment. And if you formally now replace these charges qj by these differential operators, you end up with the same expression. But you have now a mixture of charges and dipoles. And then everything remains basically the same. So we here now have these mixed charge dipole systems, and I already explained the case of 3D periodic boundary conditions and the case of open boundary conditions. And of course, you also have certain applications where it makes more sense to assume periodic boundary conditions in only one direction or in 2 of 3 directions. So you have basically these 4 cases, and we also considered these. And the difference here is that you just redefine this set S. So in the 3D periodic case, you had set to the power of 3, and in 2D periodic case, you now have something like set to the 2 times a 0 in the non-periodic direction, and in the 1D periodic case, you have something like S times a 0 in the 2 directions without periodic boundary conditions. So this is now for cubic boxes, but it's of course also possible to do it with with some arbitrary box shapes, where you have given an arbitrary parallel epipede. So this is always called triclinic box structures. So we also consider this, but for this now in this talk here, I restrict to the cubic case because it's a much more simpler notation, but it's also possible to do it with such triclinic structures. So the starting point for my work then was a fast algorithm, which was presented by Michael Pippich and Daniel Potts. And it was for 3D periodic boundary conditions for charged particle systems. And we already had some very efficient methods, fast summation methods for open boundary conditions. And at this time, different methods blopped up for different types of periodic boundary conditions for charges, and you had these dipole systems. And we said, okay, maybe we can build a unifying framework with everything, where you can treat these 3D periodic boundary conditions, but also the mixed periodic settings and the open constraints, where you can compute dipole-dipole interactions, of course, also the Coulomb interactions, but also these mixed charge dipole interactions. And also we wanted to have something like an error control, for the parameter tuning, because this becomes, of course, also interesting when it comes to applications. So this was the starting point for this work. And so I now come to the 3 building blocks of the method. I think most of you are quite familiar with the so-called eval summation approach. And I roughly explain now what it does. So you start with this function 1 over r, where r is a certain distance. So this function plays a very central role in this Coulomb problem. And so you basically have 2 problems with this function. It's long range, so it tends to 0 very, very slowly. And you have this singularity here and 0. And these are 2 problems you want to deal with. And what you do with this eval summation, you split it up into 2 functions. And so basically, or in most cases, you use the error function and the complementary error function. So you introduce a 0 here, and then you end up with 2 functions. So, and the first function in red here, it's called the long range part, and it's long ranged. It still tends to 0 very slowly, but it's continuous here and 0. And the other part, the short range part, it tends to 0 exponentially fast, but you still have to deal with the singularity here, 0. And this alpha, it's called the eval parameter or splitting parameter or even scaling parameter. And it helps you to control the balance between these 2 parts. Okay, now we have this and what to do with that. So I here wrote again the expression for example for this for the 3D periodic potential. And what you do here is you simply apply this splitting in each single summit. And then you end up with a short range potential and with a long range potential. The short range potential, you can compute it directly via truncation. So you cut by a radius, let's call this r cut, and you compute it very efficiently. You still have to deal with this singularity here, but it doesn't matter that much. So you can still do it efficiently. And the long range part, it's still a badly convergent sum, but the nice thing here is you don't have to deal with this singularity. You can just keep here the terms where the norms are 0 and then simply correct for it by subtracting the so-called self-potential, which is near 0 for the dipoles, but which is not 0 for the charges. And what can you do for the long-range part? So a sum which is badly convergent in spatial domain may be very may show very good convergence in Fourier space, and this is the case here. You can compute the Fourier series. The Fourier coefficients, they are known analytically, so you can see here how they look like, and they tend to 0 exponentially fast. So here we really have a very good, converging sum in Fourier space. And this now makes it possible to do it in an efficient manner. But still, if you compute it naively and choose the parameters as good as possible, you are not that lucky again, with the complexity. So you even want more. And the idea is, in the end, to apply fast Fourier methods, FFTs, or in this case, you need the non-equispaced fast Fourier transform because your particles, they are not located at the grid, they are located at arbitrary positions. And so the basic or the core is that you can separate the source and the target nodes based on this very trivial identity. You are not stick to the differences between the particles, because you can separate the source and the target nodes, and then you can apply fast Fourier methods to these sums. In our case, we use the NFFT. I will explain later details for these methods, but this is the basic idea. And this is what is possible in case of 3D periodic boundary conditions. Yeah, everything is known analytically and you are now almost ready, but you still have some problems in these other cases, yeah, when you have some open boundary conditions involved. So what you can still do is you can go to Fourier space with respect to the periodic dimensions, but you still have, for example, you can see it here, that the Fourier coefficients are now functions depending on the distances of the particles regarding the non-periodic directions. So you can separate the source and the target nodes, but only in the periodic directions. And you still have to deal with these symmetric or radial functions here, yeah, which involved the particle distances regarding the non-periodic directions. And so the idea how we dealt with it, so here I wrote again how the potential now looks like. For example, in 2D periodic boundary conditions, you have these functions here. And the idea is to approximate these functions by a periodic function and then by a trigonometric polynomial. So you have these functions here, and for each index k, you approximate them by a trigonometric polynomial. And if you have this, you can replace the function by this periodic structure here, by this Fourier approximation. And then you really end with the same structure as we also saw for the 3D periodic case. Yeah, you have here the same, I mean, you have still the periodic and the non-periodic dimensions involved, but it's really the same as in the 3D periodic case, only that the Fourier coefficients are now approximated or computed in in another way. And but how do we compute these approximations here? The good news is that we know these functions. These functions are also analytically known to us. We can evaluate them. We can compute and evaluate the derivatives. And in most cases, these functions look like this, yeah, like something like a head function, and they tend to zero exponentially fast. So this is a very nice property. So they are sufficiently small here at the boundaries of your interval. You're looking at these functions, but you have also some functions which are not very small out here, or which are even not decaying at all. And how to approximate them? So in the first setting, it's quite easy, because if these functions tend to zero very, very fast, you can just periodize. Yeah, then you can just do Poisson summation, and you get the approximating Fourier coefficients by applying the Poisson summation formula. Yeah, you just have a periodization, you get the C infinity function, and this is very good. But what to do in this type B? So the basic idea is that you also make some periodic function out of it, but you cut the function. Yeah? You cut the function here at the ends of your interval, and then you also build a periodic function, but you leave here a little gap. And in this gap here, you construct a smooth transition. It's some polynomial of a certain degree, which interpolates here also the derivatives up to a certain degree. And then you also end up with a periodic and smooth function. You are not restricted to the case where if these functions are very small outside your domain, you can do it with every function basically. Yeah, and if you have this periodic and smooth function, you can sample it at equidistant nodes and then compute some approximative Fourier coefficients based on the FFT. And then you also have such an approximation. So this is for the 1D periodic setting, but you can also do it in higher dimensions for radial functions. And this is the case here we are looking at. You have to do some slight modifications, but it's quite easy to do also with radial functions in higher dimensions. And if you have done this, you are really in this setting where you have the same expression for all types of periodic boundary conditions. In the 3D periodic case, you have given anything in an analytically closed form. For mixed periodic boundary conditions, you compute the Fourier transform analytically with respect to the periodic direction, and then you do periodization and an approximation by a Fourier sum with the FFT. And in the open setting, you would only have to approximate your function, where the error function is involved. And then you are ready and you have the same structure for all types of periodic boundary conditions. But how to evaluate these sums efficiently? And that's what I already said. So this is the next ingredient for our fast algorithm. It's called the non-uniform or FFT for non-equidistant space data. And I will roughly explain to you the idea of this algorithm. It mainly depends on the ordinary FFT, which can compute or evaluate such a trigonometric polynomial very efficiently if you have given equidistant nodes. And the NFFT is now an algorithm which does exactly the same, but here you have replaced this equidistant grid by some arbitrary nodes xj. And it does it with the same arithmetic complexity, but I have to say here that the NFFT is an approximate algorithm. So it introduces additional approximation errors. And it is also not invertible. The FFT is invertible. The numbers of nodes and the numbers of Fourier coefficients, they are the same, but you are not restricted to that for the NFFT. You have an arbitrary number or set of particles or nodes xj, and you have some Fourier coefficients. This does not have to be the same. So you cannot expect to get something invertible. And we also have an algorithm which is called the adjoint NFFT, which realizes the multiplication with the adjoint matrix. It's nearly the same. The roles of these indices k and j have now been interchanged. So this is called the adjoint NFFT. This has also the same complexity. And we need these two methods to compute these potentials efficiently. So the basic idea of the NFFT, and here you can then also see a connection to the well-known P3M method, is the following. You have given the Fourier coefficients on an equidistant grid, so you can go to Fourier space on this equidistant grid just by using the FFT or the inverse FFT. It doesn't matter that much. And then you get some coefficients, and those coefficients are then in the end you use to approximate your function. And what you do here, you sum up translates of a one-periodic so-called window function. And then you have a continuous function which you can evaluate in arbitrary positions. And if you, at the end, want to have a good approximation of your trigonometric polynomials, you have to modify a bit your incoming Fourier coefficients. And since this here is a discrete convolution in spatial domain, you can simply correct that by deconvolve at the beginning in Fourier space. And deconvolving is dividing by the Fourier coefficients of this window function. So this is a graphical illustration. This window function is typically something like here a head. You can think of a Gaussian or of a B-spline. In case of the well-known P3M method, it's a B-spline. You can also use a Bessel function or a sinc, something like that. We are not restricted to the type of the window function. In the P3M scheme, it's always called the charge assignment function, and this is the same role here of this window function. It's compactly supported so that these sums here are short. You only have to consider the nearest neighbors. Let's say it that way, so that you can evaluate these sums very fast. So you have several parameters, the window function. You can also modify the support of the window function. In case of the B-spline, this is connected to the smoothness of the B-spline, the order of the B-spline. And we can also do something like, which is called oversampling, where you even use more translates of the window function then Fourier coefficients you have given. This is called oversampling. So you can make even more exact because you sample the function more dense. And this oversampling is also not present in the classical P3M scheme. So we are now ready. Now we have this algorithm. Yeah, again, I wrote it here. So we do not think again about this short range part. You can do it via truncation. In the long range part, you have these Fourier approximations. And now we really have to look at the charges and also the dipoles, because now it makes a difference. These sums here, you can evaluate it based on this adjoint NFFT, which I already explained to you. But these sums, you need a slight modification, because you have to compute again also the gradient with respect to the location of the dipole. But it's realized in a very easy fashion, and it's called the adjoint gradient NFFT. If you have computed these sums, which depend on your k-space vectors k, then you can simply multiply with the pre-computed Fourier coefficients, and then the outer sums, so in case now for the potentials, are computed with the NFFT. And then you really end up with this n log n algorithm. You always not only want to compute the potentials, you also want to compute the fields, so the field gradients, the forces, for example. And in case for the forces, you also need some additional methods. You also have to compute the gradient of the potentials, and here for the dipoles, even the Hessian matrices. So you have to compute something like a vector valued, or here even a matrix valued NFFT, which is in our case called the gradient NFFT and the Hessian NFFT. And you can do it now for the experts, you can do it with analytic differentiation and also with IK, with Fourier space differentiation. So we have these two methods also here. Now a little overlook on the method, how can you use it in molecular dynamic simulation. So you have something like a pre-computation step where you pre-compute those Fourier coefficients. It heavily depends on the given type of periodic boundary conditions. And if you have pre-computed these coefficients, you run the method. And this is now mainly independent from the type of periodic boundary conditions. So you compute these structure factors by these adjoint NFFT methods. Then you have a multiplication with the Fourier coefficients, and then you, for example, compute the potentials by the NFFT, or the fields by these vector valued NFFT, or the field gradients by this Hessian NFFT method. And if you have this, you can compute the time evolution, you can compute the energies, the forces, and the torques. So here is everything you need. Yeah. And if you have then computed a time step, you can just rerun the method. But you have to look here, if you have some open boundary conditions involved, it can happen that some particles leave the box. And in this case, you have to redo these pre-computations, because in the case of open boundary conditions, the pre-computation depends on the size of your simulation box. Yes, so this was how the method works. And I, at the beginning, said we also did something like in the direction of error estimates, and we mainly looked at these root mean square errors in the forces, yeah, which is oftentimes used as a measure of accuracy for such particle mesh methods. So basically, you have two different types of errors. Yeah, you truncate the Ewald sums in near field and also in the long range part. And so there were already some error estimates for charge-charge and dipole-dipole interactions. And we also did some estimations for charge-dipole systems. And you also have a second type of error, namely the approximation errors, which are introduced by the NFFT. So you have two different types of errors you have to concern. So this is what you get here in your, if you measure the accuracy. So here I plotted the error curves for the truncation errors in the Ewald summation approach. And this is what you basically get Yeah, here I plotted the error with respect to the splitting parameter alpha for some fixed near field cutoff radius or for some fixed mesh size in Fourier space. And typically for small alpha, the error dominates of the near field. Yeah, then you have some optimum, and then the error in the far field dominates. And what you can see here, so the solid lines are some measured errors, yeah, separately for the charges and the dipoles. We looked at a quite small particle system. And the dotted and the dashed lines are here our estimates. And you can see that you can do it quite correctly, yeah, the error estimation. So this is for 3D periodic boundary conditions. This is the most easiest case because everything is given in an analytically closed form. And also these approximation errors for the P2NFFT method can be controlled quite good also for 3D periodic boundary conditions. And in the case of mixed periodic and open boundary conditions, we do it, let's say, on a quite heuristic approach. Yeah? We do the tuning of the parameters based on the error estimates we have for the 3D periodic setting. But if you do it correctly, so this is illustrated here by this picture. So we have some error curves for the 3D periodic setting and for the, here as an example, for the open setting. And you really get more or less the same error curves if you tune the parameters correctly, yeah, based on this heuristic we applied here. So we also have this error control. So this is basically all I wanted to tell you. So I've shown to you this P2NFFT approach. This is an n-log-n method, which is based on the non-uniform FFT. You can apply it for several types of boundary conditions. We extended it to mixed charge dipole systems. You can use it, yeah, and it's publicly available within the SCAFA-COS project. We are also able to deal with these triclinic box shapes with some slight restrictions, but it's not really a restriction. We just would have to provide some codes for handling these missing special cases. The software is massively parallel. Yeah, it was done by Michael Pilpik. So I have not talked about this for now. We have numerical results. We have some error analysis, mainly for the 3D periodic case, which allows us also to automatically tune the parameters. It's also supported in Espresso. Maybe some of you know it. That's the software from Professor Holm in Stuttgart and his colleagues. I think there's also the possibility to use the method in lamps, but I'm not the expert for these software libraries. So you would have to ask somebody who knows more. So I thank you very much for your attention. For those who are interested, I also listed here some publications you may look at, and we are always happy to hear if someone is interested in using the methods, or if you are or have interested students who want to implement something or work with a software. Just let us know. We are always happy if you come and ask us. Yeah, thank you very much.
Thank you, Franziska. Okay, waiting for some question. I have one question myself. So if we actually, I have two questions. So if we consider a comparison with the traditional particle mesh evil used in classical molecular dynamics, so 3D periodic boundary condition and only charges, the computational performance, the scaling I think is the same, but the computational performance are there any better, or it's really comparable?
I think it's quite comparable. I'm not that sure. I mean, you could also consult this SCAFA-COS paper, yeah, where different people were involved. They did very, I think also Godehard and Ivo have been part of this project where they compared different methods, and I think also particle mesh Ewald. So particle mesh eval, I think, or the smooth particle mesh eval, it always applies this analytic differentiation, I think, and we mainly also deal with this IK differentiation. So it makes a little difference in terms of performance, but I think basically it's the same. Yeah, you can compare it.
Okay. Okay, I see. Go ahead.
Yeah, but thank you very much for this very interesting introduction to NFFT and your method. I have a question to the non-periodic case, and since you mentioned there that the non-periodic direction is also treated by a Fourier method, so that you also have a Fourier transform, and basically it's the same formalism in all directions with a different kernel then. But yep. That reminds me a bit to this Berkowitz method, actually, which also applies the traditional eval summation in all three directions. Also, if you have the some surfaces interfaces in one direction, and they have to apply a very large setting, a very large box in order to overcome actually the artifacts coming from the periodic image in the non-periodic direction. And so how do you avoid this, and how many Fourier points do you need, or how big is the periodic box in this direction?
Okay, yeah, I see. So maybe I can explain based on this slide here. So L was in my notation the length of the box, yeah, and if you have periodic boundary conditions. And what you have to do in the non-periodic setting, you can see it here. If you have a box of size or of length L, then the particles have a distance or the difference between locations within the box can range from -L to L. So you have at least to use the double box length. Yeah. And also, in order to construct this smooth transition here, you have to add a little bit more. And then the trick is to keep the approximation, so or the error constant compared to the periodic setting. You have to use as many samples that you can scale with respect to the length of the box. So if you have a box which is 2 times larger than in the periodic setting, so you also have to use 2 times more Fourier coefficients. So if you have 30 Fourier coefficients in the periodic setting, so you will have to use 60 or even a bit more Fourier coefficients in a non-periodic direction. So we also have more work to do there in a non-periodic setting. Yeah, but it's less than 3 times larger. Let's say it that way. Yeah.
Okay, so that still keeps the amount of CPU time less than a factor of 2, I guess, compared to the periodic boundary conditions in all directions.
Less to a factor of 2.
I'm
not sure if this is
2 times the number of K coefficients, and the real space part is the same as before.
The real space part is the same.
Yeah. I mean the overall method. Yeah.
The overall, the real space part is the same.
Long range.
Yeah.
So long range might be a factor of 2 slower then, I guess.
Yeah, maybe even more, because if you have in 3 directions the double number of Fourier coefficients, then you have even a factor of 8 or something like this. Yeah.
But this is only one direction in 2D, no?
In 2D, you have to do this only in one direction, but we also deal with where you have these non-periodic boundary conditions in 2 directions, or even in all 3 directions.
Okay,
yeah?
Yes.
Then it gets even more. Yeah, the more non-periodic directions you have, then the amount of Fourier coefficients becomes larger. Yeah.
Okay, I see. Thank you.
Ben.
Yes, hi. Can you hear me?
Yes.
Okay, yeah, hi. Nice talk, thank you very much. I do have one tiny detail that you mentioned on slide number 10, about the self terms. So yes, so you say for the dipoles there's no contribution
in case of the potentials.
Yeah, we did in 2018 this cumbersome derivation of the potential energy and field for arbitrary multipoles up to any degree, and we found that they contribute, all of them contribute. This is CECAM fifth paper in 2018, and so there I would kindly disagree. It's a tiny detail in the whole thing, but maybe you should be aware of that.
Okay, maybe I can have a look at this. It's also with only concerning the Ewald summation, because this is now only for this Ewald approach.
If we that's for the Ewald,
It's also for the Ewald. Okay, that I can look this up. Thank you.
And the self terms, they live isolated, so they do not depend on the boundary conditions, etc. I would say. So because it's just the contribution from the IF on the IF locally, so it's pretty unrelated on the rest of boundary conditions and methodology.
Yes, you are correct. Yeah.
Okay, thank you.
Ivo?
All right. So, Franziska, thank you very much for the talk. I do have a question regarding the triclinic box shape. Do you know how skewed you can make the box? I mean, in a sense, let's assume one dimension is 1, another dimension is 1, and the third dimension is something like 2, 3, or 4. Is this something that would work, or is it computational more dense, or can you say something about it?
So we actually did not that much tests also for this triclinic structure. I'm not completely sure. So I did some tests, but not with such a unsymmetric setting, what you explained now. I think you can do it. So at least in the 3D periodic setting, I would say that that you don't run in troubles, but maybe I at the moment can see, because so why are you asking this question? So it seems that it is sometimes a problem for other methods. So we could
there might
try
be use case, and if you already have tests, how the computation time increases or doesn't increase at all, that would be nice to know, because for the FMM it certainly has an impact, and I'm just curious if the same is true for P2NFFT.
Yeah, you have a bit problems if the diagonal is very. You have to use more Fourier coefficients than in case of and it depends also on the angles, right? So yes, you could run in trouble if this is too bad. If the box is really. But I'm not sure how much. That I can tell you now some details.
Okay.
Also.
Well, that's fine. All right, thanks.
Godehard?
Yeah, I have another short question. You mentioned about the parameter tuning in the P2NFFT. Is it done now completely automatic, or do you have to do something by hand, let's say? I just think about you want to apply to a given problem, and you're not too much in the method. That you could just and what is the overhead then in tuning the parameters in the beginning of the simulation?
So this is still a bit a problem. So I did a lot with these parameter tuning, and I wrote a lot of scripts. I did it in Python, and I did a lot with that, but it's actually now not a part of the official software. So if really you want to do something with the method, we would have to provide some codes for these parameter tunings, because it's for now, up to now, not part of the official software. But if you have a few scripts, you can do most of the tuning really automatically. I mean, you have two different things. You can tune it to a certain error, but if you also want to have the optimal parameter combination with respect to runtime, you would also have to do some run tests in order to find what is the best. Also on your machine, what is the best? parameter combination also with respect to runtime. So it's still also, it keeps a bit experimental. You cannot do it without it. No?
Okay, just one, because you mentioned in the end of the talk that could also be run with LAMPS probably. So SCAFocus is now part of LAMPS since 2 years about. I don't think that too many people use the P2N FFT, and that would be also a very good step forward to have an automatic tuning. So maybe you could come together there and think about how to include it there so that more people could use it actually, and that get be more disseminated.
Yeah, this would be nice, but I also said that I'm now working in a little bit a different topic, and we here actually we have nowadays nobody working with the methods, and so we have at the moment also not the manpower to do something like this. But if we can come together and maybe have some discussion how to do it, this would be of course a nice thing.
Yeah, great, thank you.
Okay. If there are no more questions, let me thank again the first speaker of today, Franziska.